Hi, my name is Ali Shirsavar, and in this video we're going to talk about transformer modeling and parameter referral because we need these techniques in order to be able to design the snubbing circuits of our power supplies. So here I have drawn a transformer. I've drawn it like this on purpose because usually when we draw them as two inductors, it may cause some confusion as to the other parameters that I'm about to draw. So if you imagine that this is just a transformer, we have got some inductance, which is called mutual inductance between primary and the secondary, and that is in charge of creating the flux. So the first thing that I can do is I can add a certain amount of inductance. That is called the mutual inductance and is usually denoted by Lm. Okay? Then, if you imagine on my transformer, I've got a primary and I've got a secondary. This is a wire, and therefore there is some resistance. So, the parasitic resistance of that I can call R primary. And of course, we have exactly the same on the other side. There is some resistance on the secondary. Let's call this R secondary. Yes? And then the total amount of flux that is being generated, not all of it gets transferred to the secondary side because it is not a perfect transformer. Some of the flux will leak. In other words, the amount of current that is going through that is creating the flux, some of it is not going to link across and it's going to leak off. And that is called the leakage inductance, and that is one of the biggest culprits when it comes to creating ringing, and that's what we're trying to establish in order to design our snubber. So there we go. I've got a certain leakage. Let's call it L1 here, and I've got on the secondary L2, right? Now, here is the simplest model for the transformer. We're going to go to the next page whereby I have put some numbers in so that we can see how we can now start manipulating this in order to get a model that we can use in order to design a snubber. Now, if you imagine a flyback converter, this transformer will be sitting at the top and your switch often on a flyback is here. So this leakage inductance with the capacitance of your switch causes the ringing. And that's why we have to start manipulating this model so that we can start measuring things and start designing the snubber. So here, I've got exactly the same. It's just that I have now put some numbers in because it eases the explanation of how we're going to simplify this model. I have, for simplicity, let us say that I have got a turns ratio of 3:1. Okay? And for simplicity, let us say that on the primary side, I've got 9 volts. And if the turns ratio is 3:1, that means on the secondary side, I'm going to get 3 volts. Again, let's for simplicity assume that we have got 1 amps flowing this way on the primary. And let us assume that it's 100% efficient transformer. And therefore, if I've got 9 volts and 1 amps on the primary, which gives me 9 watts. On the secondary, I've got 3 volts. I must have 3 amps. So I've got 9 watts on the primary, 9 watts on the secondary. The problem we have here is that in order to do any mathematical analysis, these two voltages need to be the same so that we can connect this line together so that we can use our circuit analysis techniques. Now, at the moment, I can't do that. This is 9 volts and 1 amps, and that side is 3 volts and 3 amps. I cannot do much with this. So that is why we refer the parameters from the secondary side to primary, or sometimes we have to refer the parameters from primary side to secondary. So what I would like to do is I would like to change this somehow to 9 volts so that I can connect these 2 points together, and then I can do my analysis, and then I can design my circuits. And we do that by a mathematical trick. Right now, it's 3 volts. In real life, it will always be 3 volts. However, this is a circuit. I'm in mathematics world, and I can start playing mathematical tricks with this. Now, by what magic number do I have to multiply this 3 so that it becomes 9? We have got here the turns ratio of 3:1. And you can see that if I multiply this 3 by the turns ratio, it becomes 9. Okay, so I can say that 3 volts times the turns ratio, 3, is equal to 9. Yeah? Okay, this is called the secondary voltage. This one is called the turns ratio. Yeah? Now, this becomes the secondary referred to primary. And in order to show that I've played this mathematical trick to somebody else who might read this, I put a little hat on. That's called prime. So V secondary prime is the secondary voltage referred to primary. Or in other words, if you look at it from this point here, what you're going to see is the secondary voltage that has been referred to the primary. Okay? Now, this is the magic equation. If at any point you wish to refer any voltages from secondary side to the primary side, all you have to do is take your secondary voltage multiplied by the turns ratio. If you wanted to refer the voltage from primary to secondary, i.e. if you're looking at it from this side, for example, if you're designing for a flyback converter, the snubber for the diode, which sits on the secondary side, then you do the opposite. You take the primary voltage, you divide it by the turns ratio. We have got a little sheet that gives you all of these equations later that you can download. So don't worry about the details of the equations for now. But let's continue with the primary side. I'm standing on this side. I have referred my secondary voltage to primary. This 3 volts, at least in mathematics world, doesn't look like 3 anymore. It now looks like 9 volts, and it's called V sec prime. Secondary voltage referred to primary. Can I now connect these 2 points together? Well, actually, no, I can't. Because if you see now, the current here is 1 amps. 1 amps times 9 volts is 9 watts, but the current here is still 3 amps. So 9 volts times 3 amps is 27 watts. So the powers don't match at the moment. So I have to refer the current also to the primary in order to make things match. Again, what magic number do I have here that I can divide that by in order to make that 1 amp so that these two match correctly? It's my turns ratio. So you can see that 3 amps divided by the turns ratio, which for my case is 3 to 1, gives me 1 amps. So what I can say is, coming down here, I secondary prime, the secondary current referred to primary, is equal to I secondary, the real current, divided by turns ratio, which in my case will be 3 divided by 3 is equal to 1 amps, which is exactly what I want. So this current here also becomes 1 amps. So now I have got 9 volts and 1 amps on the primary. I have got, in mathematical world at least, 9 volts, 1 amps on the secondary. So can I connect this node and this node together to get rid of this transform, which is causing me the headache? Again, not yet, because impedance is defined as voltage divided by current. I have played a mathematical trick on my voltage and I've changed 3 to 9. I've played another mathematical trick on my current and I've changed 3 to 1. These will have an impact on these parameters that we discussed earlier on. We know that the impedance, in my case, is V divided by I. If I want to look at it from the primary side, the voltage referred to primary is, the secondary voltage referred to primary is V sec prime divided by I sec prime, right? That is the impedance as seen from this side. That is the impedance referred to primary. But V sec prime was real secondary voltage times the turns ratio. I sec prime was the real secondary current divided by the turns ratio. And if you do this mathematical operation, you see that you end up with V sec, that is the real secondary voltage, divided by I sec, that is the real secondary current, times these two multiplied together, N squared. And if I call this the impedance Z, we have Z prime. Impedances of the secondary referred to primary is equal to the real impedance times the square of the turns ratio. So there we go. You've got one equation there, you've got one equation there, and you've got one equation there. Please, I stress, don't worry about these. We will give you a little sheet with everything on it later on. The only thing to note is that if you are on the secondary side and you wanted to refer primary parameters to secondary, all the multiplies becomes divides and all the divides become multiplies. Okay. Now that we have referred these parameters to the primary side, we can now use a Bode 100 and make some measurements in order to identify in particular LM and the leakage, because these are the stuff that we need for our power supplies, and we're going to do that in a different video. So now that this point is 9 volts, this point is 9 volts, this point is 1 amp, this point is 1 amp, and all the impedances have been referred correctly, I can actually get rid of this awkward thing in the middle so that I end up with just a very nice lump parameter circuit so that I can do all of my calculations. So we can see that we can connect that to there and that to there, and that actually goes out of the picture. So if I draw this now from scratch, on the primary side, I have some parasitic resistance, I have some leakage, then I have some magnetizing inductance. There we go, that is my primary resistance. Then I have my leakage on the primary. Then I have got my magnetizing inductance. Then I have my leakage of the secondary referred to the primary. That is what the prime here means. And then I have got my resistance of the secondary with a prime referred to the primary, and that is the simplified model of the transformer. And now I can use this in order to do my calculations for my design, for my snubbers. For example, as I mentioned earlier, for a flyback, the FET will go there, and in fact, this leakage plus that leakage referred to the primary is the bit that is causing the ringing with the capacitance here. The diode sits on the other side, but now you can see that awkward transformer has been taken out, and therefore we can do all our calculations just as normal inductors, capacitors, and resistors. Thank you very much for watching, and we're going to talk about that in the next video.